Okay, so this talk's going to be split into three parts. I'm going to introduce how Satalia thinks about AI and builds AI solutions for large organizations at scale. Then I'll hand over to David and Charlotte to talk in more detail about the case study that we have. And I just want to thank everybody who's been part of that project. I know we've got some PwC people in the room, some Satalia people in the room. Just massive thank you for the past several years working on this project. It's been a really great experience. Okay, so before we get into AI and definitions of AI and how Satalia thinks about AI, I want to take you through this technology stack. And I'm going to make this quite interactive, so hopefully you're still nice and warmed up. But the first question I want to ask you all, can anybody tell me what data is? What is data? Anybody? What is data? Very good, excellent, unprocessed information. So it comes from the Latin word datum, which means given things. It's stuff. It's the fabric of our universe. It's ones and zeros. It's bits and bytes. So if I say to you 210280, this is data. If I say that it's a date of birth or a sort code or how much money I have in my account, then it becomes information. And one of the biggest challenges we have in computer science is taking all of this stuff, all of this light and sound and text, and figuring out what does it actually mean. So if I tweeted right now, my laptop is sick, what does that mean? My laptop is, I do have to do the arm movement, sick. Huh? What does that mean? If you're under 21, it probably means it's very good. If you're old like me, it means it's very bad. So how you interpret data is very important for then the decisions that you make. So for me, data is symbols. It's just stuff. Imagine if I give you a spreadsheet, and in the spreadsheet it has three columns. It has a column which is the date, a column which is a temperature on that date, and a column which is the number of ice creams that I sell on that date. Date, temperature, ice cream sales. What do you do with that information? What do you do with that spreadsheet? What do you do with that spreadsheet? Huh? Analyze it. Okay, so let's draw a graph. So if we have increase in temperature along here, an increase in ice cream sales along here, what would our graph look like? I know you can do this, come on. Huh? What does the graph look like? Good, yes, we see some sort of trend going upwards. This is descriptive analytics. We're organizing information to find patterns, to know things about the world. And I would argue that knowledge is organizing information to know things. We know that when it gets hotter outside, we sell more ice creams. And we could do something really cool now. We can do a thing called linear regression, which means put a line through it. And now what we have is predictive power. Okay, so we have predictive power. So if tomorrow is 22 degrees outside, I can look at my model and I can see how many ice creams I need to manufacture. And I can take this model of the world, this knowledge, and I can put it into a factory. And I can now have my factories manufacturing ice creams based on this knowledge. But can anybody tell me why we sell ice creams when it's hot outside? Why do we sell ice creams when it's hot outside? It's not a trick question, huh? Okay, so I'm inside. It's hot outside. It's not usually in the UK, but imagine it's hot outside. What's the first thing that happens? Huh? I'm inside. It's hot outside. Huh? What happens? I go outside. And why do I go outside? Vitamin D. We like the sun. It's a scarce resource in the UK. Then what happens? Huh? We get hot. And then what happens? We buy an ice cream. What do we do with the ice cream? Do we put it down our pants? What do we do with the ice cream? Eat it. And why does eating an ice cream cool us down? Thermodynamics. Okay, to expect a computer to understand that narrative from this line is impossible. It doesn't understand that humans like vitamin D and we can cool ourselves down in lots of different ways, which is why it's super important that you bridge people that are really good at finding patterns from data with people that have domain knowledge, with people that can understand and interpret those patterns. So I would argue that understanding is interpreting knowledge to create the right narrative of the world. And actually, your domain expert's going to say, Daniel, your model of the world here is wrong. Because if tomorrow is the hottest day ever, what's my factory going to do if tomorrow is the hottest day ever? Come on. Huh? It's going to manufacture lots and lots of ice creams. But what will really happen if tomorrow is scorching hot? Hottest day ever. Huh? Nobody's going to go outside because you can't reach an ice cream fast enough to cool yourself down. So the model of the world looks more like this. And as I said, one of the challenges is trying to interpret the world perfectly so we can make good decisions. And I would argue that wisdom is utilizing our understanding to make good decisions. And this is data-driven decision-making. And at the moment, every company that touches this stack is calling themselves an AI company. It's okay to do that. You get more clients and you get more money from VCs. But this isn't quite AI. I just want to talk about the top of this pyramid right now. talk about decision making. It turns out that humans are not particularly good at decision making, and I'm going to ask you a few maths questions now. So imagine these are all staff members. I don't know if anybody has staff members and can recognize any of your staff members with these 5 Pokemon, but imagine we know everything about these staff members. We know their skills, their preferences, we know whether they're male and female. And what we want to do is we want to line up these staff members that satisfy some rules. So, for example, you're not allowed to have the same colours touching, or flying Pokemon have got to be the right of other walking Pokemon. Can anybody tell me how many possible combinations there are of these 5 staff members? So we're looking at one combination. I can flip 2 around, I get another combination. Flip another 2 around, I get another combination. How many possible combinations do I have? Good, yeah, 5 times 4 times 3 times 2 times 1. 5 factorial, that exclamation mark we learned in school. It's got 120 possible combinations, some of which will satisfy the rules. Many won't, but only one will be the best one. Okay, let's make the problem a bit more complicated. So I've got 15 Pokemon. Can anybody tell me how many possible combinations there are? Don't say 15 factorial, that's cheating. How many possible combinations? Millions? Yeah, okay, so there's over 1 trillion possible combinations. To expect a human to solve this problem, we're wasting our time. In fact, one rule to take away with you today: anything more than 7, don't use a human for. Okay? Whether you're trying to figure out how to spend marketing money or allocate staff or route vehicles, anything more than 7, humans are useless. And actually, industry don't have problems of this size, they have problems of this size. So can anybody tell me how many possible, 500 Pokemon, can anybody tell me how many possible combinations there are? Guess? It's a big number. So it's a number that's over 1,000 digits. And just to put this number into context, this is how many atoms there are in the universe. Okay? And I would argue that you could probably solve problems up to about 7 if you're a smart human being. You could probably hire quite a smart computer scientist, graduate computer scientist, that can solve problems up to about 50 or 100. But if you want to solve problems like this at scale, you need a different set of skills I'm going to talk about in a second. But I want to just drum this problem home. Imagine I've got my ice cream van, and my ice cream van has got to deliver ice creams to these 24 points around London. And actually, humans are quite good at solving these spatial problems. So if we wanted to draw a path around these 24 points that saves us the most amount of petrol, maybe we'd start here and go here, and after a few minutes, we'd have quite a nice path around those 24 points. But how long will it take a computer to get the shortest path, the optimal solution? Seconds? Milliseconds? Okay, we played this game already. It's 20 billion years. So if you put 24 times 23 times 22 into your calculator, you get this number. And if you can have a computer that could look at 1 million routes a second, that could check 1 million routes a second, it would take longer than the age of the universe, 20 billion years, to go through every single possible one and say, this one that I looked at 20 billion years ago, this one's the shortest one. You should do that one. And if I had another point to the map, I've now got 25 times 20 billion years, 5,000 billion years. If I had another point to the map, it's 26 times 5,000 billion years. These are exponential problems. We hear the word exponential a lot when we're thinking about AI that can solve problems exponentially, but people fail to realize that we have thousands of these types of problems in industry that are exponentially difficult. And we have human beings solving them most of the time. So when Satalia thinks about building systems, we think about these 3 things. First of all, is the data available to help us find the insights, using machine learning, using data science to find the insights that we need from the data. But ultimately, we want to make decisions. And decision-making is traditionally an optimization problem. And I would argue that organizations right now are going through their digital transformation. They're getting all of their data together. They're throwing lots and lots of machine learning experts at it, data scientists at it, to try and find patterns. But they're failing to realize you have to leverage that understanding to make good decisions. And I would argue that there are only about 3,000 really strong optimization experts around the globe. It used to be called operations research. It matured in academia about 20 years ago. Then everybody got excited about machine learning. But actually, there's about 3,000 people in the world that are really good at solving these problems at scale. And if you build a system that has these 3 things, that you give data to, you put it through a model, it makes a decision. Tomorrow, you give it the same data, it makes the same decision, same data, same decision. You have automation. But can anybody tell me what the definition of stupidity is? Okay, making the same mistake over again and expecting a different answer. I would argue that most systems in production are autonomous and are stupid. In fact, there are actually 2 definitions of AI. One I think is a popular one, but a little bit weaker than the second one. So the most popular definition of AI is getting computers to do things that humans can do. And the reason why this is popular is because humans are the most intelligent thing that we know in the universe. And when we start to get machines to do things that are traditionally only in the domain of human beings, like understand natural language and recognize objects and images, we then attribute that as being intelligence. When we start to get to machines to do things that are traditionally only in the domain of human beings, we call that AI. And the reason why I think that this is a bad definition is because benchmarking humans against machines is a silly thing. Because humans can find patterns up to about 4 dimensions. If I throw a ball at you in 5 dimensions, you're probably not going to be able to catch it. Machines can find patterns in hundreds of thousands of dimensions. If I asked you to solve problems beyond 7, you're going to really struggle. And computers can solve problems hundreds of thousands of different elements. So benchmarking humans against machines, I think, is a weak definition. The stronger definition of AI, for me, comes from the definition of intelligence. And there's a very, very elegant definition of intelligence, which is goal-directed adaptive behavior. Goal-directed in the sense we're trying to achieve an objective. We have an objective or an optimization problem we're trying to achieve, whether it's to sell as many ice creams as possible or to allocate our staff as effectively as possible. You have to have a goal. Behavior is how quickly and frictionlessly can I move towards that goal, but the most important word in this definition for me is adaptive. If your system is not making a decision and then learning about whether that decision is good or bad and then changing its own internal model of the world, I would argue that it's not strong AI. And I've seen very, very, very few enterprise systems in production that are able to make a decision, learn about whether that decision is good or bad, and adapt its own internal model. That, for me, is the true paradigm of AI. Systems that are able to adapt in milliseconds as opposed to months or years. And with the project with PwC, we've solved this component. We've solved this. We can optimize staff at scale. And the next challenge is how do you then look at whether those staff have worked well together, whether they work well in teams, work well with clients, to then ultimately be able to optimize them better in the future. So ultimately we want to build adaptive systems, but building adaptive systems is extremely difficult. And I think I'm probably going to hand over now to...
All right. Thank you, Daniel.
That's all right.
Thank you. Daniel has talked about the enormity of the problems that are out there, and Charlotte and I are going to go into some depth about the enormity of the problem that we have solved, and the thing that we took from an idea through proof of concept, and I mean proof of concept, we didn't actually know whether we could do it, to pilot, to production in the UK, across our firm in 2 years and 2 months. And I think you'll agree with me when we're done that was a terrific accomplishment. And that's why I'm so proud of the entire team, many of whom are here, both from PwC and Satalia, and will be available afterwards for the Q&A. So the problem that we solved is this one. So we solved the problem of scheduling over 4,000 people to over 8,500 projects, or as we call them, engagements, in the UK firm. And the good news about a constrained optimization problem is that when you solve it, when you get it optimized, not optimal, because you never get it perfect, you get to have more of all the things that you want and less of all of the things that you don't want. So what we wanted is we wanted to maximize demand fulfilled. We wanted, as far as possible, every single one of our projects to be fully staffed if possible. We wanted to distribute the workload evenly amongst our people to improve their quality of life and their opportunities. We wanted to minimize the travel time, which is also a quality of life issue. It's also an environmental issue. It reduces our carbon footprint, and it's just a cost. Unnecessary, necessary travel is great. We're all here. Unnecessary travel is just waste. And the fourth one is actually really interesting. So midway through, it wasn't one of the ones that we started out to solve. Midway through the project, someone had the bright idea of adding this one. And I'm sorry, I don't mean that sarcastically. It actually was a bright idea. And they said, look, there are gaps in the schedule. Susan is free half a day here. Fred is free for 2 days there. What if we could clump the free time? And this was one of the things that we added that was incredibly successful. We ended up with, Charlotte, was it 11? On average, 11 weeks of free time as single blocks of a week or more per person, which was fantastic. Now, it's a hard problem to solve, not only because of all the permutations and combinations you're talking about, but we also had a whole bunch of constraints. Now, those of you who are the optimization experts in the room will know that it's not really a clear binary thick line between whether something's an objective or a constraint. You can talk about some of them either way. I'm not talking about that. I'm talking about the way we understood the problem, not the way it was implemented, right? So what we did is we said we want to accomplish these 4 things. And at the same time, we have to deal with all of the constraints. We work in a number of regulated environments. We have to conform with a whole bunch of regulations and laws. We have a whole bunch of business rules that we've put into place to keep our quality where it needs to be, to treat our people well, etc. And there are some things that are just a bad idea, like putting me on an audit when I'm not an accountant. I mean, when I joined the firm, I was really worried about the numeracy test that I had to take. And my boss said, don't worry, don't let your team down, but don't worry, none of us have passed it. So we had, originally we thought there were 30 of these. Charlotte will tell you more about how it ballooned. So what we had to do with each one of them, each objective and each constraint, is we had to state them in English. And we first thought there were 30. When we got into it, we found that the English wasn't that clear. It wasn't rigorous enough to build something around. So the first part was simply getting the language really, really accurate, so that there were no contradictions and there were no gaps. Then for each one of the goals and objectives the same, and constraints, it had to be expressed mathematically, then it had to be expressed in code, and I'm going to click that so you can't take a picture because I don't think it's real anymore. It's an old version. But every one of them had to do that, and then of course all of those pieces of code had to work together. So we did that, and it worked. In fact, it's working right now. We've just completed another cycle and is running as we speak. I was in the office one day, and someone came over and said, David, do you have a minute? I want to show you something. And they showed me this, and it was really clever, because we have lots of clever people, and they do all kinds of clever things. And they said, we've created a game. And the reason this is so clever is because it's really hard for us to understand the enormity of the problem. Daniel's thrown some numbers at you, I've thrown some numbers at you, but it's still really hard for us as people to understand how hard this problem is. So this looks like a really simple problem. You've got 4 people, you've got 1 week, you've got 3 locations. Okay? And what you need to do is you need to make sure that every shift is assigned, everyone gets a day off, and everyone is qualified. I looked at this and I said, great idea to create a game, great idea to help people understand what it is. It's too simple. And they said, try it. It took me 6 minutes. It's supposed to take 2. Right? I stared at the screen for 3 minutes trying to figure out what to do with it, because there are a bunch of things that make it non-optimal that I'm not going to go into today. But it was a massive learning experience for me to really understand how, your rule about 7. And most people, when they play us, it takes them 2.5 minutes. I've seen one person do it in 1 minute. The computer always does it in 1 second, and it always gets the best result. And so the reason I wanted to talk about this is partly because it's a really good anchor to all those really big numbers that, as Daniel said, we really don't understand. But also because this was a game that we first modeled in Excel. We then built it in Mini-Zinc, Charlotte keeps me honest, Mini-Zinc and Python, in about 2 weeks. So as much as there are a whole bunch of massive, big, complicated optimization problems that are out there that take the kind of effort we're talking about today, there are also a whole bunch of really little ones that probably don't take a lot of time, probably don't take a lot of effort, and are probably worthwhile doing. So to tell you how we got there, I'm going to turn over to Charlotte, someone who is one of the many people who did all the real work and all the hard work. Please welcome Charlotte Byrne.
Thank you, David. So to take a look at our journey to date, PwC and Satalia have been working together for over 2 years, and it's been a really exciting and transformative journey for us as a business. Our project has gone through 3 main areas, such as the proof of concept through to pilot, through to a full production rollout. However, over the 2 years, there's been a number of other stage gates and lessons learned for us, some of which I'll take you through today. So 2 years ago, when we decided to work with Satalia, we knew we wanted to do something around workforce optimization. What we weren't sure is what exactly we wanted to do. So we brought them in and we started collaborating and running some workshops in understanding the art of the possible with their technology, while also speaking to a number of different areas in our business and understanding their processes and pain points. From this, we established some selection criteria over the complexity of the technology, the impact we wanted to have, and how difficult of a challenge we were willing to take on. From this, we picked an area of the business that was most there in terms of operational and data readiness, but was also one of our most optimal areas of the business already, which set a real challenge for us in being able to increase efficiencies. But we thought if we're able to create efficiencies in this part of the business, we'll be able to create it across our whole network. Once we decided on the use case, we began carrying out research with 2 separate business units. In our organization, each business unit, while they collaborate, they work and operate somewhat independently and have their own kind of rules and procedures and ways of working. And what we were trying to do is build a single solution to solve this problem for multiple. So in doing this, we needed to drive change. Trying to drive change within areas of the business without having any benefits, research, or even knowing if it's going to really work at this point was a significant challenge. Going out of this research, we captured about 30 of those constraints David spoke about to bring into a proof of concept, where we accounted for the business rules, the operations, and organization processes. We applied weightings and prioritizations to each of these. For our proof of concept, we ran the schedules through our solution in parallel with the business as usual manual process so that we would have a benchmark to begin being able to measure the opportunity at hand. One of the key learnings from the proof of concept was the 30 rules that we had developed were effectively not enough. There was a number of nuances within the businesses that weren't clearly defined business rules or formal processes. They were just simple ways of working and behaviors that we hadn't accounted for. And once we accounted for these, refined the solution and added more rules, it took us from 30 to over 60 rules in our most latest release. During the pilot, when we were creating, after the proof of concept was successful, it gave faith in the product and that it was able to produce schedules that we were able to use within the business. It also gave us something to begin to measure what success looked like. We took this through to the pilot, where we removed the manual business process for 2 business units, which account for approximately 800 staff within our organization. We ran these schedules probably, I think, about 18 months ago. And from this, we took some key lessons. One was the data. We integrated into over 7 source systems and 100 data points. A number of these data points, our individuals within the organization were responsible for maintaining. And when people are responsible for their own data and what you're inputting, quite often you're working with incorrect or historical data. But once the business and people on the ground realized the impact that this was having on their day-to-day lives, where they were going to work, the teams and portfolios of work that they were getting, the quality of our data significantly increased overnight. So after a successful pilot to 2 business units and 800 people, we decided to challenge ourselves as a project team and go from 2 business units to 4, taking it from about 800 people to 1,500. And we started refining the rules, adding new parameters that we needed to in order for it to be acceptable by the business. And 4 months before go live, we had a very senior and ambitious member of our team say, "We've done it successfully for 2, I don't want 4, let's go for 13, taking it from 800 people to over 4,500. With 4 months notice and no move in the go live date. So this was a real challenge for us in scaling up what we had built, not just in terms of the business rules and parameters, but the infrastructure. We had built custom APIs to consume all of this data into the solution. When you're pulling data for 800 people, that's one thing, but when you're scaling it overnight to 4,500, the number of data points we were pulling from, this had a significant impact, and we had to refactor parts of the code and all of the APIs to ensure that we could consume it and how we needed. The challenge to roll out to 13 business units was set. We ended up rolling out to 11. And this was because we felt that there were 2 that simply weren't there as we got closer to go live in terms of data and or operational issues. Some might see this as a slight failing. However, I see this as a success for us as a project. We could have put those areas of the business live and through the tool, but taking that understanding of the impact of the technology and what it will do to your organization and being able to decide when it's not right was something that we're quite proud that we took that call to do it. And at the moment, back in the office, we're doing another annual planning process that's going live, hopefully by the time I get off stage, to another 10 of our business units within the organization. the future. So what are we planning to do moving forward in our collaboration with Satalia? At the moment, we're looking at how we can build a more dynamic, real-time solution that we can use on a daily basis to create updates to reflect the ever-changing dynamic organization that we have at PwC. What can optimization do for you? So what we've managed to solve over 2 years is an insanely large workforce optimization problem that has taken 2 years. As you've seen from the tool that David showed in the game, there's a number of much smaller problems in every organization, taking Daniel's rule of 7, that AI and optimization can be used to solve. So maybe for some of you here, it might be useful to take away and start where we did back 2 years ago in those workshops, and simply sitting down and analyzing your business and how it operates and trying to identify any areas of challenge and having a think if AI or optimization could solve some of these problems for you. So that brings to an end our presentation for today, but we will be here on stage. I don't believe there's a talk after ours, so if anyone has any questions, feel free to come up to us. Thank you.